All right. Welcome to the session 2 of the lecture 6. Welcome to the session 2 of the lecture 6. We are going to continue, and in this section we are going to see a new things, and that is very important. Okay, to know. There is a term, very important term, that is called the Kolmogorov complexity of the data. What is the Kolmogorov complexity? What is the Kolmogorov complexity? Look, if you have a data, so you can think that you can write a program that can generate this data. Okay. So Kolmogorov says that the complexity of a data, I'm talking about the complexity of the data, but how complex my data is the length of the shortest computer program. Okay, because if you write a 2-line program that can generate an infinite amount of data, so length of the shortest computer program that produces it as an output. This is the Kolmogorov complexity. So I'm not going to tell you that how to find out the Kolmogorov complexity, but can you just see these two things and tell me that which has a more which particular item has a more Kolmogorov complexity? 1111 and then 000. Can anybody tell which one has a higher complexity? Same. Okay, correct. Some students are telling same. Yes, because you only have to change to 1 and then it would be producing the same thing. So therefore the complexity is same. So now can you tell the second one, that all the ones, then at some place there is 0, which has the higher complexity? That one, because now you have to this has a higher one. Okay, because now you have to, for the first, just compare the first string and the second string. Tell me who has the larger Kolmogorov complexity. You can say the second one has a larger complexity. Correct? Okay. Now can you compare the first one and the third line, first one and the second one? Can you compare the second one? So you see that in the third line, again the second, the right hand one has the higher complexity, and you can see that even it has a smaller size. So data, if the data is big, it doesn't mean that it has a more complexity. Understand? Kolmogorov complexity says that even if this data is smaller, but it has a higher complexity, because to generate this we have to write a different program. Okay. Then in 1978 there was a concept by Jorma, and it says that the goal of statistical inference means whenever I am going to find out, to learn something from the data, what should be my goal? My goal should be to find out the regularity in the data, and then it can be identified how I can say that how well I am into the finding the regularity, that how can I compress it, how much I can compress. If I can compress more, it means that I am better to find out the regularity. If I can find out the regularity, I can do the compression. To find out the how good you have learned can be seen as a how well you have compressed the data. What does it mean? Goal of the statistical inference should be to find out the regularity in the data. I mean, how you find out the regularity. If you find out the regularity, then you can compress, and therefore you can say that if you can compress more, it means that you have better algorithm. So in this sense, you can say that learning is a data compression thing. If I say that given the data you learn it, so you are actually data compressing. If you can compress well, then you are learning good. Okay. So let me see this data and try to see some very important concept using example, and let's see this data. And here, what is the data? It contains the 4 characteristics. One is the outlook, how is the temperature, how is the humidity, how is the wind. I call them X1, X2, X3. And then whether I want to play the sports, some sports is there. Whether I want to play cricket on that day or not. It is sunny, hot day, high humidity, and wind is weak, then I'm not going to play it. This is some play. Okay, you understand. So this, are you able, can you see this data? So each tuple can be represented as a set of attributes pairs, because you can say, if you say the first line, so you say that x1 is equal to sunny, x2 is equal to hot, x3 is equal to high, x4 is equal to week, and y is equal to no. Sorry, your voice is more breaking after video is on. Okay, so I'm going to close the video. Okay, hope it would be better. Okay, so you see that sunny, hot, high, and weak, and place. Similarly, here it is written that the data is this: x1 is equal to sunny, x2 is equal to hot, x3 is equal to high, and x4 is equal to weak. You see here. And similarly, the next data item is sunny. I think there is a typographical mistake. It is sunny. Okay, sunny. Okay. So you understand this data, okay? So you understand this data. So this is the data you have. Total number of different attribute. How many different attribute values you have? Can you tell me how many different attribute values you have? Attribute value means the sunny, overcast, rain. Okay, overcast again. You not take sunny, rain, sunny. So sunny, overcast, rain, hot, mild, cool, high, normal, strong, weak. So these are the things. So how many different values? 10 values you have. Okay, 9 values. You have 10 values. Okay, try to see. You have 10 values. So each tuple has a 4 attribute that could be chosen at most out of 10 things. You let's assume that I put 10 things somewhere, and each to create one attribute, you have to choose 4 of them. So how many you can choose? 4C4 ways, 4C4 different attribute pairs you can create. Okay, different tuples you can create, and it comes out to be 210. And since class could be yes or no, so you put 2 ways over there. The total number of ways are if for one line you write, then you write yes. The one write again same line, write no. So these are all the possible way of having the data. So there are 210 multiplied by 2. So what is the code length of this particular? What should be the length of the code for one? Somebody is asking how it is 10. You find out. Let me just check if I'm wrong. Okay. Somebody is asking how it is 10. Let me just check. So can you be with me? Okay. So I take the sunny. Okay. Then I cut all the sunny over here to this I have because I had taken sunny. Then I take overcast. I cut overcast from all the places. Then I take rain. I cut rain from all the places. There go 3. Okay. So 1, 2, 3 things we have. Then I take hot. So I cut hot over here. Then I take mild. I cut mild over here, mild over here, no mild. Then I take cool. I remove all the cools. Then I take high. I remove high. I'm not going to consider it. How many different things are there? I just want to say so. High. After that, I have a thing normal. Okay, normal. Then I take a weak. I remove weak from everywhere. Weak. Then I take a strong. I remove strong from everywhere. So if I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If I have these 10 things, okay. If I have a set where 10 things are there, then to create this thing, so how many different combinations I can create? 10C4 because I can take 4 out of them. Some of them would be irrelevant. Just forget about them. Some of them are irrelevant, therefore they would not appear into the data. That is altogether different story. But using these 10 things, we can create 10C4, that is 210 different rows, and for every row we can write yes and no, and therefore becomes 420 different rows. So whenever you create a database using of this kind of setting where these values could be there, you only say that 420 different values are possible, or your database would be having only a subset of this, correct? So let's assume that somewhere you have written all these 420 things and you have assigned a serial number 1, 2, 3, 4, 5, 6, 7, 8 to 420. Then to create a database, you just need not to write complete thing. Nah? You just take what is the sequence number. You just write that sequence number. That is enough because you want to create a database, and in your database only 5 things you want to take. So don't take the complete. Don't put the 4 things. Instead of 4 things, you just put the serial number of those things. Are you with me? So I'm telling that what I'm telling is this. Okay. Okay. 1 minute. What I'm telling is this, that in what I'm telling is this, that you have 10 things, and using 10 things you wrote first line, second line, third line, fourth line. How many lines you can write? 420 lines you can write. And we know that if we have written a program, then we know if I ask you what is 310th line, then you can tell that this line represents, say, for x1 is equal to this value, x2 is equal to, because you have, if you have written a program, then you can execute the same program to find out a particular line. Okay. So instead, if you want to create the database, for example, this particular database also, so all these things, how many lines are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14 lines. So this line would also be coming into this list somewhere. Let's assume it comes out at the 15th location, 15th location. Another comes at 19th location. So in this database, you only write 15, 19, dot, 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 these 14 numbers. Okay, so this is your database. So your database is going to be written like this. Instead of writing all these things, because it's a description, instead of description, you just write those numbers. Okay. So, all right, I understood that if I can somehow represent all the possibilities, then I can use their index. So okay, so to represent one number, because there are only 420 numbers, so for one number you need to represent at least log of into bits, because you will be putting them into the bits. So how many bits is required? 8.71 bits are required. Then what is the code length of this database? So 14 items are required. Therefore, 120 you multiply for each of the row can be represented with 8.71 bits. So you multiply it by 14, you get 122.01. Is it clear? Okay, is it clear? Why it is like that? Because there are 420 different numbers, and for each number you take the log. Therefore, at least this much number of bits is required. 14 different things are rows are there, so you need this much number of bits. So how much you can compress? Can anybody answer? How much you can compress? Okay, somebody can tell I can compress 10 bits, so it would be take 12. Somebody would be more optimistic. He can tell I can compress 22. It would be the after compression I can get the data after. Okay. Okay. Very important question I'm going to ask. Please try to answer this question. That how much you can compress. Out of this, how much you can compress? Somebody can tell, okay, I can compress 10. Somebody can tell 20. Somebody can tell I can compress 100. Anybody can come and he can call, I can compress 110. I am the best compression one. And next person will come, no, I can compress 120. Somebody would come, I can compress 122. So this is the highest compression that anybody can do. If somebody comes and tells that I can compress 123, you would say no, 123 bits are not there, so how can you compress 123? So maximum compression that is possible is 122. Please understand this, because this is the size of the data. So all the maximum compression would be that you compress all the things, and you need no data to represent. That is okay. How you are encoding, I'm not asking that. How you are encoding. Let's assume that there is some very good encoding. What is the maximum that you can compress is 122. Okay. Now consider two hypotheses, and I'm going to use this hypothesis to compress the data. What is the hypothesis? If outlook is equal to overcast, then play is equal to yes. If its humidity is equal to normal and wind is equal to weak, then play is equal to yes. So what does it mean? It is a code, because H1 is a code. And using this thing, you need not to now have the data. You just take the data, you just put it here, you would be able to see that whether yes or no, and then you would be right. This is another hypothesis, that is three rules. Output is equal to overcast, humidity is equal to normal, wind is equal to weak, temperature is equal to mild, humidity is equal to normal. Then you tell yes. Means if outlook is equal to overcast, you say yes. Humidity is equal to normal and wind is equal to weak, you say yes. Second hypothesis, Outlook is equal to overcast, you say yes. Humidity is equal to normal, wind is equal to weak, you say yes. Temperature is equal to mild, humidity is equal to normal, you say yes. If any of them is satisfied, you say yes. Otherwise, you say no. What is the hypothesis of what is the length of first hypothesis? How to represent this hypothesis is a difficult thing because how many different values we had. Because to represent this thing, you have to find out how many different things are possible in this way. 10 things are possible because your outlook is equal to you can put 10 values over here. No? So out of those 10, you are actually having one over here. So therefore, 10 log of 10 C1. What is the length of for this? What is the length of this? Log is always on base 2. Okay. Humidity is equal to normal, wind is equal to 2. Here 2 things are there. So you see out of 10 things you are choosing 2. So 10 C2 and then you take the log because those many possibilities are here there and you are only specifying one of them because humidity is equal to high, wind is equal to weak. How many values you can specify humidity is equal to, wind is equal to? Because at this place you can put 10 values and here also you can put 10 values. The possibility was this 10 C2. Okay, 10 C2. We are just selecting 2 things over here and we are putting into here. So length of first hypothesis is 8.81. Length of the second hypothesis, similarly, there are 3 things. So you put all these things, it comes 14.30. But this having only this hypothesis, you cannot represent the data because they are going to do the errors. Look, and you use the hypothesis 1, yes, 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 yes. Yeah, these places it says yes, and hypothesis 2 tells these places it is yes, and otherwise it tells no. Okay. So you have to find out that how many places the hypothesis first is right and second is right. So if it is wrong, what is going to happen? That you also have to tell that okay, this use this particular rule, but this is an exception. That if this condition comes, you have to don't follow the rules. The exception so that you are always right into the database. To represent this database, you would apply this formula. But you would not apply this formula to the places where this hypothesis is going to give you the wrong results. So where it is a wrong, no, no, it's right. At this place, yes, but it is telling no. So there is one error. No, no, yes, yes, no, no, and yes, no. So 2 places there is an error. For to the yes, it says no. Okay. There are 7 places it was yes and it is also telling yes. Okay, correct. Similarly, for the no, all the places where there was no, it is telling no. No places it is telling yes. So this is the confusion matrix for the hypothesis 1. Similarly, you can see that how good the hypothesis second is. That for 8 places which were earlier thing was telling yes, it is also telling yes, and 1 place it was telling yes, but it is telling no. Can you find out that place? Yes and no. This is the place where the hypothesis 1 and 2 both are doing error. And here it was an error, but the hypothesis 2 does not have this error over here. All right. So how many bits are required for exception? Okay. Out of 7, yes, you need not to represent anything. 7C0 because you need not to represent anything. But here there are 7 things. No, but 2 are actually 2 have the problem. At 2 no places there is a problem, so you have to code them that at these places don't consider my no. 7C2. Okay, similarly here at 8 places everything is right, therefore 8C0. But for places where it is no, you would be telling one place. Out of 6 places where the algorithm says no, you would be putting for one place there is an error. So 6C1 possibilities, you are taking the log of that. So therefore the length of the error exception is going to be 4.39 and length of the exception going to be here 2.59. Okay. Now again let me go to the original equation that we want to find out how much compression we can do. So we can do the compression after doing the compression, how much bits I can save. Okay, so originally how many bits we have? 120. You know now we have done the computation here. 122. So this value is 122. This value is 122. Then the length of hypothesis, and length of hypothesis about how much? This was the length of hypothesis 8.81. So 8 point and minus 8.81. and then you have to code for this exception 4.39. You put over there, so you find out at 108. This is the maximum compression this is the compression you get, and with the hypothesis 2 you get the compression of 105. Very important concept. It tells that the result shows that H1 has a better compression than H2. Hypothesis 1, which actually does more errors, has a better compression than the H2. So on the information theoretical viewpoint, from the information theoretical viewpoint, you are not going to select the H2, because although the H2 is better algorithm, but you are not going to choose H2 as an output. You are going to choose H1 as a algorithm, better algorithm. Okay. So we should stop generating the more rules, because more rule is generated with the H1. We have more generated one more rule to get H2. So we should stop generating more rule and deliver H1 as a good hypothesis model. That is a very important point. So ultimately, what we have seen here, that to represent this data, we can propose these two hypotheses. One hypothesis has the more, this hypothesis 1 has a less number of rules, hypothesis 2 has the more number of rules. Therefore, to code this hypothesis, you need more steps. H2 needs 14.30 bits and H1 needs 8.81 number of bits. You understand this thing. But H1 hypothesis does more error. Therefore, to represent the errors, you have to write 4.39 bits. You have to use 4.39 bits of exception, because the places where it does errors, you should write so that at those places you can correct the database. But for H2, since it is a better algorithm, you need lesser number of bits. But when you put into the complete formulation, means how many number of bits you have, you can do the compression. So overall, with the overall number of bits, you subtract these two values, 4.39 and the. Let me just write out this formula for you. So let me just go back here and okay. So you, in this formula, you just see that what is the value. Okay, what is the length of this is? What is the value of this thing? This thing is 122. What is this value? H1. From here we have seen that 3 point. This is 4.39. This is 2.59, and we have seen that to encode the hypothesis, how many bits is required? To encode the hypothesis, we know here we need only 8.81 number of bit, but to encode the S2 we need 14.30 number of bit, and this value is again the same 122. So by this we got this value. Okay. So information theoretical viewpoint, you want to understand information theoretical viewpoint, that you are generating an algorithm, a hypothesis. You are generating a hypothesis. Which hypothesis is better? Although this second hypothesis has less error, but you are going to select the hypothesis 1 from the information theoretical perspective, because it gives you better compression. Are you with me? Are you with me? Are you with me? Okay. This is important thing. Thank you very much. So this is important thing, that although I have a better algorithm, but I would not go for that better algorithm because it is not compressing the data much. Okay. Now I have the question: how do we say H1 has a better compression? You see that how much compression you can do, because you have to represent these things I have written over there. Na? At this much number of bits you have to require, and you have to need to number of bits to encode the exception. You need some of the bits to encode the hypothesis, and their summation is the higher for the H2. Therefore, H1 gives you better compression. So this concept is over. That this what was the concept? The concept was that you are selecting, given two hypotheses, you would select a hypothesis that has a better better compression ability. Number one, we are going to see a different concept now. This is the Markov model, and Markov is just a name. Okay, just there is a very simple thing that let's assume that you have x, you are into the state x0, multiply with the vector with the matrix A, you go to the next state. Then you again multiply the same, apply the same operation, you are going to change the thing. Again apply the same thing, your state is one by one changing. But whatever you are applying the same thing. For example, एक दिन बाद क्या हुआ, एक दिन बाद क्या हुआ, एक दिन बाद क्या हुआ. Today is a hot day. अगले दिन क्या होगा? What is going to happen the next day? Or and how the things are changing? It is fixed. There is some underlying phenomena. वही phenomena we are going to put over there. Seeing what is going to happen to the next day. Then next day is this. Then what is going to happen next day? So this is the Markov model. Here things are fixed. Initially there is some, you are into some state. You are applying some phenomena, and therefore your state is changing one by one. Your state is changing. Correct. So it assumes that future is independent of the past given the present. Means if you want to find out xn, given x minus n, you can find out what is xn. Means if you want to find out x5, given the x4, you can find out x5. Or if you know the matrix A, you need not to find everything what has been happened earlier. The assumption is that the present state encodes all the history. That is important. That is important assumption. So what do I mean by this? I mean by this, let's assume that you are into state A0. Let's assume that you are into state A1, then you state A2, then you state A3, A2, then a state A3, A4, dot dot dot. Your state is going to change one by one. If you want to find out if you are into the state A3, and if you are into the state A3 and you want to find out what would happen into the next thing, you just apply the matrix that was actually applying over there. You need not to, if you know that you are into the state A3, you know the underlying process that is going to happen, you multiply that, and this by this you will be going to get the A4. You need not to, you did not require A1 and A2. This is what important thing that I want to tell, that this is my assumption that the present state encodes all the previous history, and therefore you need not to do this. Okay, so sometimes people also talk about what is the order, because for example, how different data. Here I am only taking one thing. Okay, so it's order one. If I say the order 2 Markov, then I need to take the two things, and we are not going into that detail. I'm just going to take the simplified model where I'm telling that one thing is sufficient. Okay, independent things are not independent because everything is connected. Previous things are connected because A is multiplied over there. So thing independent, all the values are not independent. Most of the time it is used for the temporal data such as weather prediction, speech recognition, automatic music generation, handwriting recognition. Many places it is applied. And we are going to see an example. Suppose a company is selling a product A, soap, okay, and it has a market share of 20%. Okay, Patanjali has a Patanjali A is Patanjali. It has a market share of 20%, and it launches an advertisement campaign, and that is extended, that is expected to retain 90% of the पुराने लोग को रखेगा, and old customer, and attract 70% new. Okay, 70% new people इसको मिलेगा. So what maximum market share the product A can gain? Okay, question is that product A ka market share, what is the market share of product A? Is 0.2. State 0 is 0.2, means A ka state is 0.2, and what is the state of A dash, means of other product people are asking is 0.8. Okay, this is a 0.8. You understand this time? 0.2 and 0.8. Product A has a market share of 0.2, 20%. A dash means everything that is not into the A has product share of 80%. And when something has been launched, what is going to happen? 90% of people are going to retain over here. So A to A, this matrix says A to A is 9.9. So it is also possible that some people are leaving, means 0.1% would, after the advertisement also the people are not going to purchase this item. So 0.1 is that they are not going to purchase this item. And 70% new people, A to Okay, so 0.7%, 0.7 means 70% new people are coming. So 30% people are going to be retained over A dash. This is what the transition matrix is. Can you see this? Okay. So somebody is asking, please go to previous slide once. Need to check the question. Okay. So let's see this. Is it clear? Suppose a company selling a product A. You take the printer screen, please. Okay. I'm going to next slide. Is it done? Take the printer screen. All right. So I'm telling that 90% items are there, then 0.1, then 0.7, 0.3. So this is the transition matrix. So what is going to happen that initially this was the case, but initially S0 was this. But when you multiply this thing with this matrix, what is going to happen? It is if you multiply S0 with A, means advertisement campaign has been launched. You are going to get 74% of the people. Okay, 0.2% because 70% you are one down. The total should be one. Total is 1 in all the direction. Yes, total is always 1. Where is the total is not 1? Okay, so when you multiply this thing with A, you get this kind of 0.74, 0.26. Can you see this? So if you multiply this, you are going to get this thing. Okay. Then again, if I launch the campaign, what is going to happen? If I launch the campaign again, then with this S1, if I again launch the campaign, I get 0.84, 0.152. Again, I launch the campaign 0.86 and 0.1304. So you see that in the first time the increment was very high, the second time it was less, and third time it was even less. Okay, things are changing very slowly. So let me just introduce one more concept so that everything is clear to you. There is a concept of stationary matrix. What is a stationary matrix? That you take AB and you multiply with the A, you again get AB. So can you solve this equation? So let's assume that we have 0.71 and AB. You can find out what is the value of A and B. You can multiply 0.9A plus 0.7B is equal to A, and then another equation would be 0.1A plus 0.3B is equal to B. Then you can solve this equation. You can find out the value 0.875 or 0.125. So what does it mean? That after applying multiple number of time, there would be some scenario when this A is 0.875 and B is 0.125. Then if you multiply this with this matrix, you are going to get the same matrix. Means things are not going to change. There is a stationary point. You have reached to the stationary point. So you see that if you keep multiplying, you cannot expect that at some time everybody would be purchasing my item. There will be at least some people who would be purchasing other items also. So does it always happen? Means this scenario always happen? No, only if the matrix is regular. And regular matrix means if some power of this matrix has all the positive values. For example, this is a regular matrix where all the values are not 0. This matrix is also not regular because if you whatever number of time you multiply with the same matrix, you are not going to get that. I ask you that to you work on this, that whether it is a stationary third one is stationary matrix or not, and try to find out that is there a power that gives you something that all the things are actually non-zero. Then it is also a regular matrix. So you go ahead with this. Okay. So you got the idea. Okay. So what is there? What is going to happen? So this is the Markov model. Markov model assumes that the same things is going to apply. You see that initially you are into the X0 state, then you apply some phenomena, then your state changes, then your state changes, then your state changes. You keep doing this until now. You keep doing this. But there is a very important concept that is called the hidden Markov model. What is the hidden Markov model? Hidden Markov model says that actually what is happening into the system, you don't know what are the underlying processes are happening. For example, if I want to predict the weather, okay, so how can I predict the weather? Because I can only measure how the things are happening. We don't know the actual equation. because God is doing something, that therefore something is happening. We don't know. God knows only what are the actual parameters. We only see the observation what is happening over there. No? We see that on that day there was some other matrix, and therefore we got some observation. Ki kitna dhoop tha, whether it was a sunny day or not on that day, what was the climate, and etc. These things we can, weather, etc. We can find out these information. So we don't know that what is the value of H0. Sometimes we have some other matrix, that matrix is multiplied and we get the observation. Similarly, we don't know what happened into the next day. We only apply, we get some observation only. So actual model is this. Actually, you understand? The actual model is this, that there is some underlying state, some underlying phenomena that has been happening, and we don't know that what is the state, but we know these observations only. Okay, and only observation is given to me, and we actually want to find out what is going to happen the next. Okay, assume we observe, and I have an example, that assume that we observe the coverage, small, medium, large, of some news articles, such as I open the newspaper in the morning and I see that what is the coverage on coverage on snow, coverage of rainfall, coverage of say क्या कहते हैं उसको, coverage of say snowfall, coverage of snowfall. You just want to see what is the coverage of snowfall. If lot of news coverage is there, then you say the small coverage, so large coverage. If small coverage means there is small column on the snowfall, then you say small coverage, medium coverage, and large coverage. Let's assume that we can find out whether the small in today's newspaper, what is the coverage of the snowfall. Okay, some news article I am specifying. Let's assume that we are finding out the small, medium, large, to know whether a day was hot and cold. Okay, so let's say somebody asked me that what has been happened 100 years back. I may not know what has happened on that day, but I know that I have access of the newspaper on that day. And using that newspaper, I want to predict that whether that day was hot and cold. So let's assume that this is a scenario. On a hot day, the probability that it would be a small coverage is 0.1. On a hot day, probability that coverage is mean is medium is 0.4. On a hot day, the coverage would be large is the probability 0.5. On the cold day, the coverage would be small is 0.7 probability. Coverage would be median is 0.2. I just put all these values randomly. Therefore, don't care about them, that what the value are. You just assume, just familiarize yourself with what they mean. On the cold day, what is the probability that it would be a large coverage? 0.1. Let's assume that this is like this. Okay. And also, let's assume that we know the underlying phenomena, that if it is a hot day, next day is going to be hot. Let's assume be 0.7. It is a hot day, next day is cool, 0.3. It is a cold day, next day is hot, is 0.4. It is a cold day, next day is cold, is 0.6 probability. Okay, let's assume that these are the probabilities. Okay. All right. And let's assume that the initial configuration for hot and cold be, let's assume on some day we know that the probability that it's a hot day is 0.6, and therefore the cold probability that that day is cold is 0.4. Okay, and let we have the observation. What observation we have? We have find out the news articles, and we have seen that someday it was a small on this this was the initial day, na? And on that day it was a small coverage, then medium coverage, then a small coverage, then large coverage. We find out. Okay, this was the observation that we have, because we have a newspaper. We have seen that this is the observation. This was the thing. Now we want to find out what is the probability that it was a hot day, then cold day, then cold day. What is the probability? Okay, can you find out what is the probability that it was a hot day, then cold day, then cold day? That's very easy. Okay. What is the probability that day is hot? We know that 0.6. What is the probability that on the hot day, or it is a small coverage, hot day, small coverage, 0.1. Okay. Then this hot to hot, next day should be hot. What is the probability that a hot day next day is hot? 0.7. Hot day is hot, 0.7. Then on that hot day there is a medium coverage. What is the probability on the hot day? It's a medium coverage 0.4. 0.4. Then from hot day you want to get a cold day. From the hot day, cold day, the probability is 0.3. You see 0.3. On cold day, what is the coverage? Small. On cold day, coverage is small. Probability is 0.7. Okay. And from cold day, next day is cold day. What is the probability? It is cold day, next day is cold, and the cold day, next day is cold. Probability is 0.6. This is here. And then on that cold day, it is a large coverage. What is the probability? Cold day, large coverage 0.1. You find out this probability. So you can find out that what is the probability that it is hot, cold, cold. Correct? So you similarly you can find out what is the probability. All their days are hot and hot, cold, 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 cold. You find out all these probabilities. Okay, you can find out. Okay, because we have computed one value, na? Hot, cold, cold, hot, cold, cold, hot, cold, cold. We have find out this value 0.001212. This value we have computed very recently. Similarly, you can find out all these values. Is it clear? Now you can find out their summation, and then you can divide by the summation, so that all these values, the summation becomes 1. That is anyway, that is not that much important, because so that summation becomes 1. Okay. So which is the most probable? Can you find out which is the most optimal state sequence? Which particular sequence has the most probability? Yes, you see that here is the highest number because these are the values. This is 0.29. Somebody is telling CHHH. No, CHHH is 0.11. CCCH is 0.29. So you see that. So you find this way you can say that the probability of this particular state, that first day is cold, next day is cold, next day is colder, next day is hot, is the highest. Now this is a dynamic programming approach. This is the one approach that is a dynamic programming approach. You find out all these values and then you find out the thing. Hidden Markov model says that I would what is the probability on a particular day that this is going to be hot or cold, the first day, whether it is going to be hot or cold. So you just find out, because at these places it is hot first day, and at these places first day is cold. You find out the summation of these numbers. Okay, these numbers. Find out the summation of these numbers and find out the summation of these numbers upper, and try to see that which is greater. If you find out the summation of these numbers, it comes out to 0.18, and you find out the summation of the bottom things, it comes out to 0.88. Similarly, at the second place, if you want to find out whether it was a hot or cold, so you find out the summation of these four values. Then you find out the summation of these four values, and you find out, therefore, the second place you find out summation of 4 plus 4, these 8 places. And here you subtract by 1, or you can find out the summation of these 4 and these 4s, last 4, to find out what is going to happen into the second place. Somebody is asking, sir, what is the normalized probability? Normalized probability, initially you find out none, all these probability, then you find out the summation of all these values, and then you use that value to divide all these values. And if you divide all these with the summation, you are going to get these values. That's called the normalized probability. Okay, so that the summation becomes 1. Now here, at the 0th day, first day and second day, at the third location, if you want to see, if you want to find out whether it should be what the probability of head and probability of hot and cold, you find out the summation of these two things, then these two things, then these two things, then these two things, and you see all the summation is going to be 0.2287. So let me just once go to the slide, and you can just paste it and just tell you. So let's assume that you want to just to explain this thing a bit. Let's assume you want to hunting for the third place. Okay, for the third place, for the head this thing, for the head this thing, you take these things. For the head you take these things. Third place, here it is a head, and here it is a head. Okay, you find out the summation of these things, 4 things, and their individual summation to find out what is the probability of head. Can anybody find the solution? Find the summation for me. Please help me to find out the summation. 0.04, 0.0032. Can anybody find out the summation? and then 0.005, 0.004, 114, so on. Can anybody find out? If you are working with me, you would be getting this value. You would be getting 0.227988. Okay, you would be getting this value. And similarly, if you find out the summation of these things which had not been circled as a green, then their summation is going to be this number. Okay, so this is this thing. So this is the Hagen-Markov model approach. Hagen-Markov model says that first you find out this probability, then for all the each of the place you find out what is the probability of getting here, H and C, and hot and cold. You see that the probability of C is more, so you put the C over that place. For the second place, you see the probability of getting hot day is higher than the second one. You see H, and therefore here you see that the probability of C is more, so you put C, and here the probability of H. So hidden Markov model approach says that the probability of this particular day is the highest according to the hidden Markov model. What is it? Is CH. Is it clear? Is it clear? CH. Are you with me? So okay. So that's all for today. So I think this is going to be the last math heavy class. I need to cover all these topics because if anybody asks you what is the hidden Markov model, what is the mathematical concept of description length, and then you should be able to tell what is PCA and what is diagonalization, mean variance, curves of dimensionality. These are very important topics. You should be able to tell. So most probably this is going to be the last math heavy class, and next class you would be able to see more applications. And this class also have many applications, such as what I told you that every matrix you find out SVD, and what is the application. I told you that using this epsilon you can find out how many different concepts there, means how many logical uh, logical clusters you should make. So it gives you an indication. So using this you can find out. Then we have tried to see that sometimes when you are getting data, it may be very high dimensional. So you should do something to control the dimensionality. And one method is how, if you can find out the manifold that has generated this data, you may be doing very well. We have also seen that there are negative impacts of the curse of dimensionality, and that our data becomes very less. Whatever number of data you have, it becomes very less if your dimension is very high. We wanted that whenever we have a data, so all the rows should be linearly independent of others. So if this is the case, then our covariance matrix, that given the data, if you find out X transpose X covariance matrix, it is going to be a diagonal matrix if all the things are independent. So it would be a diagonal matrix. What does it mean? That given the data, if you multiply its transpose with itself, you are getting only non-zero values into the diagonal, and all other value would be zero. So given the data we want to, then therefore our objective would be, given the data we want to transform in such a way so that covariance matrix becomes this diagonal matrix. So what would be the advantage? That it means that I am into very good shape. I don't have any problem. Okay, so one way to do this is to use the eigenvalue decomposition. We have seen that if given the data, if you find out X transpose, do the eigenvalue decomposition, try to carefully construct X transpose X, then you can get the matrix. This second matrix, now given the X, you can find out the Y. How can find out given the X you can find out Y? You find out X transpose, you find out X eigenvalue decomposition, then you use X transpose to multiply with the X to get the Y. This matrix would be this very special matrix that it has the covariance matrix as a diagonal matrix. So it is a very good thing. But the problem is you cannot decompose everything every time. You cannot find out the eigenvalue decomposition. So is the problem. Then the solution is use SVD, because because you know that SVD can be found for every matrix. So using SVD, if you use the U and you use the U transpose X, given the X, you find out U transpose X, then again you are going to get that special matrix, and this is called the principal component analysis, PCA. You say that given the data, it becomes a PCA of this. And this matrix has so with the same thing, it gives you the diagonal matrix, because sigma square is a diagonal matrix. So you get this very important characteristic. So what in terms of the understanding we are going to get, understanding is this, that given the data, you are going to get two axes because all the values are changed. Therefore, the data get translated and rotated, and the new data that you are going to get would have the maximum variance into all the directions, and therefore things would be independent. Okay. We have given some example, two example, one that this carefully how to write. You please go and write this on the Python to see that whether the same output you are going to get or not. I have told you that how I created this data, and similarly this here the code itself is generating the data. You can increase the number of points and see how the things are changing. Okay, and by yourself you can find out the different linear combination over here and try to see that what is going to happen. In this data, we have seen that one of the column was linearly independent of other, and therefore the PC has given you that if you only use 4 components, you would be getting 100% of the variance. It shows that if you apply the PCA, then very easily you can that these components are useless, and we can reduce the dimensionality by this much factor. Okay. PCA has been applied into the facial images, and we have seen that it has first applied into the 1991, and it has achieved very high accuracies onto a special database that has images of only 16 individuals, 96% of the accuracy. How they did? So every image was converted as a single line, and then PCA is applied. New kind of images was called, that was called eigenfaces, and using those eigenfaces, they have done the thing. Also, we have seen that a maximum description length concept that tells that we want to find out an algorithm that compresses the data most. Given two hypotheses, one of them, if it is compressing more, I would select that algorithm as a best hypothesis. So out of two hypotheses, I would select that algorithm that has a better compression things. Kalmogorov complexity, I try to include you, and you can see that this smaller string has a high Kalmogorov complexity. I'm not going to tell how to find out how much it is. This is beyond our scope. So we have seen an example where we had a data, and we have shown that how many what is the maximum number of bits is required to store this data is 122 number of bits is required, and we have seen two algorithms, and we have seen that to code this particular hypothesis we need 8.81 bits. To code second we need 14.30, and since the algorithm will be doing some errors on the data, therefore we have to also put the exceptions, and those exceptions took 4.39 and 2.59 bits respectively, and therefore overall compression achieved by the H1 and H2 are 108 and 105. So we have concluded that although the hypothesis 2 has less error, but on the information theoretical evaluation, it was not a better algorithm. So we should not go beyond this. And most of the time, better if it is not a better algorithm for the training data, it is fine, because on the places where generalization is needed, it's better. It would be going to be better. For unseen things, for the seen thing, it is better, as to. For the unseen things, it would be wrong. So therefore, we should go for the estimate. Okay. So we have seen this. Also, we have seen that the Markov model gives you a understanding that if you tell me what is the state, then I need not to understand that what has been happened earlier, and there is a fixed process that is always applied, and therefore the state are changing. So we have seen that if an example that tells that after some time things are going to be saturated. Okay, we have seen hidden Markov model. That is a very important model applied at many other places. It actually tells that what is the underlying state and what is underlying process. We actually don't know. We actually have the observations. We don't know what is happening into the system. What are the real variable into the parameter into the system? We don't know. We have some observation, and we therefore have a model. So therefore we have to go by that. and therefore we have seen this example where there was some let's assume that there is some coverage on some snowfall, and small coverage, medium coverage, and large coverage on some day. Yeah, you put randomly some numbers on hot day, probability of small coverage, medium coverage, large coverage. I give these things, and I know the underlying change that particular probability that given a hot day, next day will be hot day, cold day, we can find out this thing. So these two things are important. If these two things are given to me, and then I can find out the what the probability. An observation is given to me that on the paper it was small, medium, small, large was given to me, and then if I want to find out what is the probability of hot, hot, cold, cold, then I can somehow do something to find out it. So we have seen this, how to find out this probability. Then we have seen that in the dynamic programming approach, the probability, highest probability is 0.29. Therefore, the probability is CCCH. But into the hidden Markov model, for every day it apply, it will find out the summation of the probabilities and try to see what is the probability of that day being hot or cold, hot or cold. So therefore, hot and cold, the probabilities are this. Therefore, the more probability of this day to be cold. The first day is cold, next day is hot, next day, third day is the again cold, and the fourth day is again cold. So therefore, the probability of this thing is going to be sorry, it's hot. Okay, CHCH using this formulation. So this is all that we have today. So any questions? I'm going to stop the recording now. You can keep asking the questions.